Good morning, everyone. Thanks for joining us for our presentation today. Our topic is Schneider Electric Conext Energy Storage Solutions, brought to you by AEE Solar. Before we begin, if you are experiencing any technical difficulties, now's the time to sort them out before we begin. So you'll see on your screen to the right-hand side, there's a control panel. There should be a questions box there. If you have any questions about if you're not sure you're seeing the right thing or you can't hear me very well, go ahead and type in your question there and we'll sort everything out before we begin. And while we wait for everyone to join on, I'll just make a couple of quick notes. We will have our Q&A session following the presentation. So you're welcome to submit your question at any point during the webinar, and we'll do our best to answer as many as possible after the presentation. And again, you can use that questions box in the control panel to submit your question. There will also be a brief survey that will pop up in a new window once you exit the webinar. If you could just take a couple of minutes and answer, I think there might be 5 questions. We will send you a copy of the presentation slides a little bit later today. So really quick, we'll only take you a couple minutes. We just ask your feedback on this presentation and topics you'd like to hear more about in the future. We want to make sure these are as valuable to you as possible. We know your time is limited. All right, well, looks like everyone's joining on and I don't see any questions, so I'll introduce our presenter today. We have Mike Swenson, Schneider Electric's very own Senior Sales Application Engineer. Mike, I'm passing the presentation over to you.
Thank you, Hannah. Earlier this year, in February, Schneider Electric introduced 3 new products. One is XW Pro, which is an expanded version of our older XW series. The other is a gateway that gives us a lot of communication and interface capability. And the third one is Insight 2, which is a cloud-based system that allows customers to look at the performance of their system remotely. Okay. So what we're going to do is go through the different products and also the applications along with some AC coupling sort of comment. So we're going to do just some stuff on Schneider, a quick go over of the products and compatible products, do some stuff on architecture, AC versus DC coupling, and then some methods of AC coupling. Schneider's a pretty big company, about $27 billion in sales last year. We have about 160,000 employees in 120 countries around the world. And this is just sort of a breakdown of where we are and what we're doing. This is an overview of the various products that are in our CIB division, the XW Pro, the XW, the European version or the export version, the Conext XW, which has both a domestic and an export version, a couple of our charge controllers, the MPPTs, picture the gateway, and Insight 2. And then there's some breaker panels and various control stuff for generators and a monitoring system. As we get more and more into systems that employ lithium-ion batteries, the battery monitor providing state of charge information is going to be more and more valuable. The primary purpose of the design of the XW Pro was to have a Rule 21 compliant offering for California, a PREPA compliant offering for Puerto Rico, and a HACO 14 compliant offering for Hawaii. We needed to have a system that had more software space and more memory, and so we did that. We also modified the power board to use film capacitors as opposed to electrolytic capacitors, which allows us to offer a 10-year warranty. This product works pretty much seamlessly with all of the older support products like the system control panel, the old COM box, as well as the AutoGen start map. The XW is a very flexible product that can allow you to do self-consumption. It can do backup power. It can be used off-grid. We've done microgrids with it, and we can do self-consumption. Probably the most common installation is residential backup power. This is the evolution of the XW. First XW came out in 2006. It was the first pure sine wave inverter. Some may say, well, what about the trace sine wave? The trace sine wave actually had 56 steps, and it only became a sine wave when we put a load on it. It was the first that had a 120 volt, 240 volt output, so it could be connected to standard residential electrical panels. It had dual inputs, one for generator and one for grid. It had a 60 amp 240 volt transfer switch, and it had 8 millisecond transfer time. The other thing that didn't get fit into this slide was that it had power factor corrected charging, so it wasn't nearly as noisy electrically as the old phase control chargers. Then we went to the XW in 2014. It had lithium battery capability. It was scalable to 76 kilowatts in 3 days. It was set up to do what we call multi-clusters, and it had an AC coupling capability. The movement to the Conext XW Pro, which was February of 2019, was, as I said, Rule 21 compliant. It was capable of working with the new gateway and Insight, and it can deal with solar charge controllers, interface better with some of the optimizers, etc. So this is sort of a rehash of the other one, but the main thing was Rule 21 compliant. HACO and PREPA will be coming very soon. It basically is an incredible reliable system. Return rate on these guys is like 0.02%. We can do single phase 120, 240 systems or 3-phase systems at 120, 208. We can stack them for 61 kilowatts worth of AC output capability. And we are very efficient, actually, for a battery-based system. And then we can work with all of our other devices. So these inverters basically can perform 3 general functions. One is it converts DC to AC. So you have batteries, which are required for this device, you can basically provide 6.8 kilowatts continuously. So that means that if you put a 6.8 kilowatt load on the inverter, and as long as you have DC power, it will supply that load. You can run 8.5 kilowatts for 30 minutes, 12 kilowatts for 60 seconds. That's basically the surge capability to run well pumps, motors, etc. The output voltage is 120, 240 plus or minus 3%. The second thing that we can do is we can take AC provided by a generator or the grid and charge the battery. And so that in that way, we're an AC to DC converter. We can do 3-stage charging, which is optimum for flooded lead acid batteries. We can charge up to 140 amps, and we can basically charge all of the different technologies using either the flooded, gel, AGM, lithium ion, or custom setting. The third thing that it has the capability of doing is it has the capability of selling power back to the grid. So if you have it set up in, say, a backup power mode where you're really not using the energy for the loads, you can sell that power that you generate from the PV back to the grid. And so it basically, you set it up for what battery voltage you would like it to operate at, and then it will basically sell 240 volts back to the grid at a amount of power that you set it up for. The fourth thing that it does is it has an internal transfer switch, which allows you to feed the grid power directly through the inverter to the loads. And then some of that grid power, quite a bit of it actually, can be used to power the battery charger. The 60 amp pass-through is also about 8 milliseconds. So we don't see any loss of power to the loads when we do the switching. So the key values are basically, we feel that we have a higher return on investment with the Rule 21 compliant systems, where we do a tremendous amount of testing for reliability. We can do just about any kind of battery-based inverter connections that you like, from DC coupled, AC coupled, various architectures with lithium-ion batteries. We can do fairly detailed monitoring. We can troubleshoot and upgrade firmware with the Conext gateway, and the units are field serviceable. I always love easy to install because that's basically in the eye of the beholder. And I think you guys could probably tell me more about whether it's easy to install than I can. I know that some of the folks say, well, it's pretty heavy, and that's basically because you're doing line switching at 6 or 7 kilowatts, so you need a pretty decent transformer. So the products that right now off the shelf are compatible with the XW Pro are all the common devices. We have the Conext Insight 2, which you can log into for free. It's not a charged cloud. We use a configuration tool to set up the system for stacking or multi-cluster. The gateway is a very powerful device. It will be used to do BMS control going forward with lithium-ion batteries that are what we call closed loop. That means that they have a port on them and they want to control the charger based on the internal data that they are gathering. And then we can also connect multiple units together. This is a picture of the gateway and also the insight. The gateway, not all of the features that we expound upon are available in the gateway as we speak. We've got a roadmap to make it full featured by year end. For instance, you see the little antennas there. The Wi-Fi function is not completed yet. I think it's going to be ready in September. There are some of the Modbus capabilities that haven't been implemented yet. And so it's not quite full featured yet, but it will be, like I say, by the end of the year. And then the insight, basically, with the COMBOX, we had some issues with security and encryption. And so we wouldn't allow complete control of the system. In other words, being able to change the settings and stuff like that without doing port forwarding, which was a pain, to say the least, because you had to get the internet service providers on board. With the Gateway and Insight 2, you'll have the full capability of going to a site, changing values, checking out the status. You can basically look at all your installs in a map and basically see if any of them have had any trouble overnight or whatever when you get in the morning. So it's a pretty powerful little system, and like I say, it's available at no charge. So this is all the different stuff. We have charge controllers, a 60 amp 150 volt, and an 80 amp 600 volt for MPPT charging. We have monitoring, which is the gateway, along with the battery monitor. The interesting thing about the monitor is that it doesn't give you the granularity of the EMS in the battery. It gives you a battery bank capability, but it gives you state of charge, and it's a very accurate state of charge, which once we get the state of charge implemented in all the devices, can be a very powerful tool in determining when to start generators, when to switch over to the grid for charging, a number of other things. If you notice in the lower right-hand corner, there's a pre-wired system, which we call Conext Quick Fit. And there are 7 versions of that implement different charge controllers and different inverters. And then there's one that basically does not have a charge controller and is set up for AC coupling. And so you can basically just get a pre-wired system, hook it up to the wall, connect it into the sub panel, and with your PV inverters also connected to that sub panel, you have a quick install AC coupled system. And that leads us to AC coupled application. Compliant with NEC 690-11 and 12, which are arc fault and rapid shutdown. So most of you guys, I'm probably covering territory that you already know, but in the latter part of 2010 and earlier, we did a tremendous number of string inverter, PV inverter installations that powered the loads, and then any surplus power was sold back to the grid. And they gave us pretty good programs to sell power back. In some cases, they were too good and were dropped as soon as they expired. Ontario rings a bell. So this is basically how the PV inverter was connected up to the main panel. What we're finding is that there are a tremendous number of customers that would like to add storage to these existing systems, and which we're calling retrofits, and we're doing them quite frequently. Some of the problem related to that, though, is the how old and capable the PV inverters are to do an AC coupling. So this is a comparison. This is on the left, there's a DC coupled system that basically takes the power that's stored in the batteries and runs the load, and then the batteries are charged by a charge controller running off the PV. And so in an AC coupled system, what we do is we charge the batteries initially off the grid to get them charged up, and then basically we will charge them from the PV whenever the grid goes away. And so the power back feeds into the output of the inverter, and then it's stepped down and applied to the battery. And this is an example of using the inverter as a grid former. So as long as there's PV available, or as long as there's grid available, the grid passes through the internal transfer switch in the inverter, goes to the sub panel. The PV inverter sees that as a reference and provides current back to the loads and to the grid, basically as long as the grid is there. And so we can see here that the grid voltage can charge the batteries, it can run the loads, depending upon how much load it is. If there's plenty of PV power, then it runs the loads and is sold. When you have a power outage, then the XW turns on and seamlessly, basically. So likelihood is that the PV inverter will never even see an interruption in power, and it will then form the grid from the batteries, and the PV inverter will continue to operate. However, it has no way to sell power back to the grid. So whatever surplus power is created is backfed through the inverter and is used to charge the battery. Well, that's all well and good until the batteries become fully charged. Then, because this is an unregulated charge, both current and voltage are unregulated, we have to figure out some way to protect the battery. And so early on, we used a function that was IEEE 1547 anti-islanding, where we basically would simply turn off the grid former by shifting the frequency from 60 hertz to 60.5 hertz, which would then shut down the PV inverter, and then we would go back to a 60 hertz output. We would wait 300 seconds, 5 minutes, and then start back up again. And we would do this very slow oscillation. It wasn't necessarily bad, but you could definitely lose some water in flooded batteries. Right? And so the Rule 21, okay, basically created a frequency ride through, which basically said, okay, I'm going to supply power to the PV inverter between 58.5 and 60.5 hertz, and it would operate continuously. But as the battery voltage would go up, the frequency would ramp up, and we would retard the output of the PV inverter. In other words, the goal was, if you had full batteries, to retard the PV inverter to the point where it was only supporting the load. And so if you had a 5 kilowatt inverter and you had 2 kilowatts worth of load, you wanted to retard it by 60%. And that was done by ramping up the frequency. We got the frequency up to 62 hertz. It would then operate similar to the old anti-island. And so this graph basically shows power out and versus frequency, and you can see as the power out of the inverter ramps down down to 0 at 62 hertz, and then it basically retards the output considerably. So non-curtailing, basically the anti-islanding, basically when the battery got up to a little bit below bulk, we would begin to shift the frequency, and then the lower graph there shows that we would just shut off the PV inverter. With curtailing, we basically bring the frequency up slowly, as you can see in the second slide, or the second graph, and then the output would be linear down to 0. And so, believe it or not, guys, this stuff works. And so it's about 20 thousandths of a hertz per second. Okay? So there's some delay, okay? Just in case the battery voltage goes back in. And then once we go up to bulk +2, we start shifting the frequency quite quickly. And so the idea is to protect the batteries from any sort of overvoltage, especially lithium-ion batteries, because they're very sensitive to voltage fluctuations. So you can see on the upper level, we bring the battery up, and then this is anti-islanding, and we'll shift the frequency and shut off the system. And this is the effect on the battery. So the battery voltage goes up, and then it goes back down once we cut off the PV inverter. And you can see on the current that the current actually will go negative because the XW is supporting the load. When we do frequency shift, again, we continue to use the power out of the PV inverter until the batteries become completely charged. And if they discharge, we come back on again and So it basically keeps the batteries charged and protected. Now, one of the things with AC coupling is you get a better efficiency because the PV inverters selling is cheaper, or is basically 98% efficient. You need to make sure that you size and select a battery that's good for the application. A lot of times in AC coupled applications, they want to use the smallest battery bank that they can, and that's not necessarily a good solution. But AC coupling meets the NEC 27 AF arc fault protection and rapid shutdown requirements, because basically when you disconnect the grid from the PV inverter, it basically shuts off, and it's within the recommended distance for the DC. So you basically automatically configure. The new PV inverters that are Rule 21 compliant have frequency watt function, which is what we're using to curtail. And therefore, all of the new ones that are Rule 21 compliant are capable of doing a good job of AC coupling. Some of the old ones, on the other hand, the Fronius comes to mind. They had a method that they used for detecting the grid that was basically they sent out a pulse. It was called impedance checking. And so they would send out a current pulse into the grid, and if the grid was connected, it would get absorbed and nothing would be reflected. But if an inverter was connected, that's a high impedance output. And unless you had loads on in the system that could absorb the pulse, it would get reflected back, and the Fronius would tell you that it's not connected to the grid and wouldn't allow production. So what we're doing now is we're retrofitting these PV inverters back into with storage to allow power production in the absence of the grid, and also backup power when there's no sun. And so we need to figure out how long they want to run their loads and all that other stuff. And there's a sizing part of this coming up. And so if they're UL 1741 PV inverters, they may or may not have the ability to curtail. They will have the capability to anti-island. If they're UL 1741 FA inverters, they will have the ability to curtail. And so you add a sub panel, you add a XW, and you add some batteries, and rewire some, and you can have basically a storage AC coupled system. So, but when you do the retrofit, you still want to size the system as though it was a storage-based system, which means that we need to have a good idea of what the loads are, okay? Because the loads determine the size of the storage-based inverter, in this case, the XW. And so peak load determines the size of the inverter, okay? And then average load and runtime determine the size of the battery bank. And then the size of the battery bank determines the size of the array. Well, in an AC coupled system, the array is already determined pretty much. You might want to add some, but not very likely. So, but we still need to know loads and battery bank size. And so, how much PV exists, that's a good thing to know. We don't want the PV watts available to exceed the XW Pro 125% rating. So you don't want to have more than about 7.5 kilowatts worth of PV, just because you're going to have a lot of surplus power. If there are, we've run into systems where they've had 30 kilowatts worth of PV power, which actually exceeded the transformer that was feeding the house. The transformers were more along the lines of 25 kilowatts. And so what we'd like to do in these large ones is see if we can break down the system into smaller parts. If they're microinverters, it's pretty easy to do. We just keep a portion of the microinverters feeding the main panel, and then AC couple with a properly sized amount. Battery size is basically sized to accept the power. So some batteries are limited as to how much current they can take. And so if we assume no AC loads, and we have, say, 5 kilowatts worth of PV power, that is a significant amount of current that may or may not exceed the capability of the battery. So, 50 kilowatts at or 5 kilowatts at 50 volts is 100 amps. And so if you only have one battery, like I say, people like to keep the battery bank size low, then that may exceed the capability of the battery. So that has to be factored in. And then a larger bank may be necessary just to handle that current, but also if the customer is experiencing outages or brownouts and would like to have a significant amount of backup power, then the battery bank size obviously will need to increase. Lead acid batteries, you need to follow the general guidelines. We discharge them to 50%. We keep the current within their specified amount. They're not good for partial discharge. And obviously, you need to ventilate them for someplace for the gas to go, and they generally use multiple batteries. Generally, you use 6-volt batteries, so you put 8 of them in series. With lithium batteries, they come out at 48 volts, and so they can do partial discharge. They can do they can accept higher rates of charge. In some cases, C over 1. So that's pretty good. Their internal BMSs can protect them fairly well. One of the worst things, though, with the BMSs is that if you exceed temperature, the battery will disconnect. Well, you don't want the inverter to see 0 volts, so you really need to be careful with making sure that the battery bank doesn't completely disconnect or shut off. So one of the things that we do to protect the batteries as well is we do the frequency shift, which is the anti-islanding. We do curtailment, which is the having the PV inverter back off, and then we'll do we can use the XW Pro aux port to operate a external relay which if things get completely out of control, we can just disconnect the PV inverter physically. And that'll be based on high battery cutoff setting. And so what makes the AC coupling compliant is basically the nature of how the microinverters are connected to the PV, and they're all within the wiring lengths, and they basically are within the voltage requirements and the time requirements. A lot of folks forget about the fact that the system needs to shut down, but it also needs to go to 0 volts within 10 seconds. So there's got to be some kind of a bleeder resistor or something that takes the PV voltage down to nothing quickly. And so modular level power may need some additional disconnects for meeting NEC 2017. A quick fit can be substituted in this case, and it basically has, a monitor on it, and it's all pre-wired. So basically, you connect to the batteries, you connect to the grid, and you connect to the sub panel, and you're done. And I think the timing that we did on some of these was that it took about 10 minutes to do the install. So that means you can do multiple installs in a day. Okay. So that's all that I have for you guys today. Hopefully that was informative and helpful. If you have any questions, please feel free to ask.
All right, thanks, Mike. Yeah, sure. We'll start off our Q&A session here in a minute. So feel free to send those questions in. We've already got a couple of good ones. Just a quick note before we do begin. If you do exit the webinar before the Q&A session ends, just remember that survey will pop up once you exit the webinar, and just answer that. So we will send you a copy of these slides later today. All right. Mike, I'll start off with the first question here.
Okay.
Does the original XW work with the gateway?
Yes. As long as you update it to the latest version of firmware, which was 1.07.
All right, great. The next question we have is the gateway Conext Insight 2 monitoring only, or can you remotely change parameters?
It does monitoring. It allows you to do software updates, and you can control it.
Great, thank you. The next question we have, does the frequency shift voltage regulation work with all grid tie inverters?
It will definitely work with, okay, so there's two things here. One is anti-islanding or, IEEE 1547. All inverters, all PV inverters had to meet that requirement. That was just, they had to be able to shut down if the grid went away for safety for the linemen trying to repair the problems. Okay, so anti-islanding is in all of the inverters going back to the very beginning. Curtailment, on the other hand, is with any inverter, certainly with any inverter that is 1741 SA compliant, because that means that it's been tested for frequency watt control. Okay, and so the newer inverters will curtail. The older inverters will definitely anti-island. And then there's a gray area in between where most of the microinverters will curtail, and some of the string inverters will. You probably, if you're going to do a